course. In this session, I'm going to talk about a new set of base function, eta-based function. Eta-based function have been introduced by using the eta function. The main property of this function is that they tend to polynomials when the frequency tends to 0. So they are suitable for solving for approximating high oscillatory function and polynomial. In this section, I want to introduce eta-based function, then I want to give you some important properties of them. Okay, so get started with the definition of eta-based function. Eta-based function denoted by phi n of t and are defined by this equation. It is t to the n minus 1 times eta of y of order the integer part of n divided by 2 minus 1. So you can see it is in base of eta function. Here, y of t equals to minus t2 times t2 for trigonometric case, and for hyperbolic case, it's equals to t2 t2. And we have some properties for eta-based function that I want to show you on the board. Okay. So we have this definition for eta-based function, t to the n minus 1 times eta function of order integer part of n divided by 2 minus 1 of y. Here we have y of t minus t2 t2 for trigonometric case, and it is t2 t2 for hyperbolic case. Okay. By using this definition, we can find phi n plus 1 of t. We have here t to the n eta n plus 1 divided by 2 minus 1 of yt. For even number n bigger than or equals to 2, we know that we have integer part of n divided by 2 equals to this, n plus 1 divided by 2. So we can write it tn eta integer part of n divided by 2 of y of t, and we can write it t times t to the n minus 1 eta and from the definition of phi n, we know that it is phi n of t. So we have phi n plus 1 of t equals to t phi n of t. Also, for phi n plus 2 of t, from the definition, we can write by replacing n plus 2 instead n, we have t n plus 1 eta integer part of n plus 2 divided by 2 minus 1 of this. And we know it equals to n2 minus 2. Now, in this section, I want to use from the definition of eta function. Remember, eta function of y can be introduced by this reference formula, eta n minus 2i y minus divided by y and minus 2. Okay. And by using the definition, it can be equals to t n plus 1 eta. Here we have this eta of y minus 2 t n plus 1. Okay, I have a mistake here. We have here n2 plus n2. It is n2 plus 1 minus 1. It is the integer part of n2. Okay, we have here minus 2 integer part of n2 minus 1 eta of y divided by y. And here y is minus plus t2 t2. The upper sign is for trigonometric case. And the lower sign is for hyperbolic case. Okay, so by using this, we can write equals to t to the n minus 1 of y minus, for even n, we know that integer part of n divided by 2 equals to n divided by 2. So we can write it n minus 1 of eta integer part of n2 minus 1, and we have here t to the n minus 1 divided by 2. I omit this by this. Okay, here we know that we have from the definition of eta-based function, it is phi n of t, and here we can write t n minus 2 eta integer part of n half minus 2. That is divided by phi 2. So for phi n plus 2 of t, we can write this equation and we can find it from this equation. Okay. We have a theorem here, and it is the eta-based function phi n of t can be defined by Bessel function as this equation. And now I want to show it to you. We know that phi n of t equals to t n minus 1 eta integer part of n divided by 2. This. Also, we know that eta function of y has this series expansion. One divided by gamma k plus n plus t divided by 2, y divided by 4, 2k divided by k factorial. Also, we know that Bessel function of y has this series expansion. Minus 1 to the k, gamma k plus, here we have n, the order of Bessel function, plus 1, y divided by 2, 2k plus n divided by k factorial. I want to use this equation and want the series expansion of eta-based function. Okay. By using the series expansion of eta function in this part, we can write phi n of t, t to the n minus 1, eta function of order integer part of n divided by 2 minus 1. I want to use it here, times 2 integer part of n divided by 2 minus 1 plus 1 omit p summation from k from 0 to infinity 1 divided by k plus divided by k factorial. And now I want to find the relationship between this function and Bessel function. So it is, we can write here, I want to show it in this form. Here we have n, the integer part of n divided by 2 plus 1. I can write here plus 1 plus k. So I should make this term here. Okay, and we know that here y of t is equals to this one. So we need it here, this term. Plus 1. Here we have minus. First, I want to show it for minus case, and then we show it for plus, positive, T2, T2. I should plus here. So here we should have t to the minus integer part of this, and also he so we can write it t to the n minus integer part of this, t to the half minus integer part of 2 times radical p, Bessel function of order 2, 4, 3. So we prove it for this case, minus T2, T2. For the case equals to this, only here we have the modified Bessel function, because here we have 1 instead minus 1 to the k, and it is simple to show that. Okay. The next theorem that we will prove is that the product of two eta-based function phi n of t times phi m of t can be obtained by this equation. We need it later for obtaining some operational matrix. So now I want to prove it. Okay. By using the series expansion of eta-based function, we know that phi n of t, phi m of t can be obtained by this 2 minus 2 times tn plus 1 minus 2, okay, time p. Series from k from 0 to infinity for tn. Okay, we continue. We have gamma k plus n2 plus half. Divided by k factorial. Yeah, and k from 0 to infinity gamma k plus integer part of m2 plus half divided by k factorial. Now, from Cauchy's formula for multiplying two power series, we can write it as 2 series from 0 to infinity, series from j from 0 to k, gamma j plus integer part of this j factorial, gamma k minus j plus integer part of this plus half, and here we have divided by k factorial. It's aj and it's there we have k minus j factorial 2, and it's k minus j. Now, by using the binomial properties, we have k plus integer part of m half minus 1 minus half j times k plus k minus j. It is easy to show. Gamma k plus half gamma k plus integer part of n2 plus half divided by gamma this one. I don't write it because it's very long. Okay, by using this summation can be transferred to this summation. Two k from 0 to infinity, j from 0 to k, j k plus integer part of n half minus half k minus j times this section gamma k plus and here we have this part. divided by k factorial. And by using the binomial theorem, we can write this summation as two k plus, it is a binomial theorem, minus 1 k times y divided by 4 k divided by k factorial gamma k plus and here by using the Legendre duplication formula and some simple computation, we can find this summation. You can see that here y for t2. Okay, and completed proof. In this section, I'm going to talk about best approximation and operational matrices. Suppose that f of t be a member of Hilbert space on interval 0 and 1, and fh be h transpose dot a be the best approximation of h out of f out of h. Here, h is the base function and a is the coefficient vector. Now, if we choose here eta base function as a base, we have two theorems for operational matrices of eta base function. The first one is operational matrices of derivative. The derivative of h of t, where the base function, the member of a base function, are eta base function, can be obtained from this equation. The derivative of h equals to d of t times h of t. Now I want to find d as a matrix, as an operational matrix of derivative. First, let me show you this theorem and obtain d for finite number of n, and then here we have n, and then we will generalize it to the general case. Okay, from the definition of eta base function, we know that phi n of t can be obtained from this equation. Yt, here y is phi2 t2. Okay, the derivative of phi n can be obtained by n minus 1 t to the n minus 2 eta, integer part of minus t2 plus t to the n minus 1 times phi2 2t, okay? And the derivative of this we know that the derivative of eta function of order, here we have n integer part, of order n is half eta of eta, a function of order n plus 1. So we can write it here. T, and we can omit from these two. Okay, let me check. Tn, okay. Okay, that's correct. Okay, and also from the property of eta function, we know that for even number n bigger than 2, we have t phi n of t. And for even number n bigger than or equals to, we have Vn plus 2t equals to t times Vn minus 1 t minus Vn t divided by this. We show these properties for eta-based function. Okay, now I want to use all of them to obtain the derivative of operational matrices. Okay, first I want to use this equation. For n equals to 1, from this equation, the first, we have phi1 equal to t to 0 eta minus of y. For n equals to, we have t to the 1 eta 1 minus 1 is 0 of by t. For 3, we have t to eta 0 of y. I want to list some of eta-based function. We have eta 1 of yt. T4 you can see here we have eta 1, eta 1, eta 0, eta 0, and the next one is eta 2. We can protect it and finish it but by eta base function of order 7, we have t6 eta 3 of y t. Okay, and now by using these two properties, I want to obtain eta base function again. Okay, for phi3, we know that here we have eta from 2, 3, phi3, we have here t2. And for this one, and here is equals to 2, we have t phi1 minus phi2 divided by phi2. For phi5, from the first one, we have t phi t times phi4. And for phi6, here n is 4. We have t phi3 minus 3 phi4 divided by and for we have this. Okay, now I want to use these relations for obtain the operational matrix of derivative of eta base function. Okay, here for n equals 1 from this equation, we know that phi1 here 0, and here we have it is better, right? Is t to the n minus 1 times t to the n, and omit this. Okay, so we have here t times phi2. For n equals 2, it will be eta 0 of 5. And here we have eta 0 equals to phi2 divided by t. So we can write it phi2 t phi2 divided by t, and we have phi2. For n equals 2, from this equation we can find 2 eta 0 of y plus, or it is better to this, t2 eta 1 of y. Okay, and from here we have eta 0 is phi dot divided by t. And from here we can write eta 1 phi4 divided by t3. So we have 2 phi2 divided by 3 is 2t. We can omit this phi4 divided by t. And now I want to use this term. From phi4 we have this equation. by substituting this in this term, t phi1 minus phi2 divided by, and we can say here phi2. Okay. I think I have a mistake here. No, it is okay, but we don't have 2. Okay, we don't have this. I don't know. For 2, 2 minus 1 is equals 1. Okay. So here we have phi2 divided by t plus t phi minus phi2 divided by t. So here we have, okay, t2 t, we have here t phi1 divided by t is phi1, and here we have minus phi2 divided by t. These two can be omitted, and finally we have phi1. So we obtain the derivative of phi2 in base of phi1, and we continue by some more eta-based function. I need it. Okay. For example, for n equals 3, here we have 3 minus 1 phi 3 derivative this. We have 2 t eta. When here n is equal to 3, it will be 0. T2 here T3 eta 1 of y. Again, we can write eta 0 from this equation, eta 0, and we can write eta 1 from this equation. And then by using this equation, finally we can find phi derivative of phi3 is phi2 plus t phi1. And for phi4, we have find this. It's enough. Okay, so if we want these results in base of matrix representation, we can write like this: phi1, phi2, phi3, for example, phi4, phi5. We have a vector, all of them, the derivative of them equals 2. We find that here the derivative of phi1 is this: 5 phi1 prime is equals to phi2 phi2. Okay, and phi2 prime, the derivative of phi2 is equals to phi1. So we have here 1, 0, 0, 0. For 3, we find that t phi1 plus phi2. For example, for this, phi3. And for this, we find that okay, it will be 0 t1 0. So for n equals 5, we find the operational matrix of derivative. In general, we can write the derivative, the operational matrix of derivative where the ij are it's better I write this because I want to find the relationship between the derivative of eta-based function and eta function, and from this we can find the element of this matrix. Zero. So for the general case, we can find this relationship between the derivative of eta-based function and eta function. And also we say that it is like this. And element, here we have 1, t0, t, and in general, we can write this in this form. 4n is even and 4n is odd. We can find it in general like this. And you can see it is a sparse matrix 2. In this case, we suppose that y of t is not 0. And we have hyperbolic and trigonometric case. But what about when y of t equals to 0? Minus chi2 minus plus chi2, t2 goes to 0. We say that the main property of eta-based function is that they tend to 0 when the frequency goes to 0. And so they are suitable for polynomial too. So for this case, I should obtain the derivative of the operational matrix of derivative in the different way. Okay, so now I want to show it for it, and it is simple because it is in base of polynomial, and we know that the derivative of polynomial is very simple. Okay. From the definition of eta-based function, we know that it is integer part of yt. If we have here 0, from this fact that eta n of 0 equals to 1 divided by 2n plus factorial. So we can write it here. We have 2 minus 2 plus 1 double factorial. So again, I want to show it for the finite number of n, and then we can generalize it to generalized case. For example, for phi1, from this we have 1. 1 divided by 1 double factorial is 1. For 2, we have t divided by 1 double factorial, which is equals to t. For 3, we have t2, 3 again, t2. Divided by 4, 3 double factorial. And for 5, we have t4 divided by 3 double factorial, and I need to show you physics too. 6. Okay. Yeah. Here, he is 0. We suppose that we say that he is 0 because in this case, we want to have 0, t2 is a polynomial, and we want to frequency goes to 0 until the eta base function goes to polynomial. Okay, so here we have zero, phi2. It is very simple because all of them are polynomial. But in the last case, we have trigonometric and hyperbolic case, and we can write it in place of polynomial. We can use the Taylor series of them, but we want to write them in base of eta functions, and we want to find the relationship between the derivative of eta base function and eta function. Here is 1, and we know that, look at this, 1 is phi1. Here, phi3, derivative of phi3 is 2t, and we know that t is phi2, so we can write it phi2. Pay attention, we can find the relationship between the derivative of eta base function and eta base function. Here we have 3t2 divided by 3 double factorial. We know that 3 double factorial equals to 3, so we have t2, and we know that t2 is equals to phi3. Here we have we know that t to the 3 divided by 3 factorial is phi4. So we have here 4 phi4. And we can continue with this in general, or for this case, we can write for example, for n equals to 5, Here we have the derivative of phi1 is 0. So here we have all of this row is 0. And here for the derivative of phi2, we have phi1. So here we have 1, 0, 0, 0. For phi3, we have 2 phi2. For phi4 is, 4 phi4. Excuse me, phi4 is phi3. And phi3, 1. And phi5 is 4 phi4. Here we have 1 phi3. Here we have 4. And you can see it is a sparse matrix. And in a computation, when we wanted to write some code for obtaining the solution of some differential equation, it helps us very much because it's a sparse matrix of order n times n. Here we have 5 times 5. And in general case, we can obtain for n when n is even and when n is odd these derivative of matrix function for eta-based function. Okay, yeah, we have a 10-minute break and then continue. The next theorem is about dual operational matrix. The dual operational matrix of h of t, the base function, can be obtained by this equation. Integral from 0 to 1 h of t times h transpose of t dt equals to qh, where qh can be obtained by this. And it is a n times n operational matrix. Each of elements here, for example, phi of n and m, can be obtained by this equation. Okay, for a frequency, for non-zero frequency, remember we find the multiplication, the product of two eta-based function in this theorem. In this theorem, phi n of t times phi m of t can be obtained by this. So it is easy to, by integration from these terms, you can find it easily. Only I want to show it for the case when we have frequency equal to 0. Okay. Here we want to find this. The elements of base function times and it is equal to this matrix. Phi n of t times phi1 of t phi n and 2t until phi n phi n. By integrating on both sides of this term, we can write it dt dt okay. For the case y of t, I told about that we can use the product of two eta-based function of order n and m, and it is by a simple computation you can find it. For y of t equals to 0, it is simple too, because we know that phi n of t equals to t n minus 1 divided by two integer part of this minus 1 to factorial. It's based on polynomial, and integration of polynomial is very simple. So we have, for this case, divided by double factorial 2 times integer part of m2 double factorial. By integration on both sides of this, you can find it easily. As this. Here we don't have factorial in this term. It's n m plus 1 minus m plus m minus 1. And the proof is complete. Okay. Now in this section, I'm going to talk about some delay differential equation, and I want to develop a new numerical method for solving a state-dependent and time-dependent neutral delay equation. Look at this equation. We have equation x, the derivative of x is equals to this function. Here, x is a real valued vector function of order rho. Also, g is a real valued function of order rho 2. And theta 1 and theta 2 are continuous function. Now I want to show you how we want to use eta-based function for deriving the approximations, the solution of this equation. Okay. Look at this. We have here J is a function, is a real vector function of order rho in base of t, x of t, and the initial condition here is x of 0 equal to x0. Okay, In this equation, delay differential equation, if we have t, this part, t minus t1 or ti for I equals to 1 or 2, ti of t and x of t. If this term equals to, for example, pt, where p is a constant between 0 and 1, we have pantograph delay differential equation. If this term t minus ti, t of t and x of t be, for example, tau of t, a function of t, here we have time dependent delay. And if here we have t minus ti, here it can be 1 and 2, be a function, for example, psi of x of t. It is in base of a state dependent. A state dependent is the function that we are going to approximate it, obtain it. We have a state dependent delay. Okay, we are going to investigate the solution of all them. And here x of a real vector function, g is a real vector function too, and theta 1 and theta 2 are continuous function. Okay, now in this section we want to develop a new numerical method for solving this equation. Okay. The best approximation, here we have, it is better to write x of t is x1, x2, x rho t is the real vector function of order rho. Also for g, we have this. Here, the best approximation of each element of xi of t can be obtained by this. Here, h is a base function, and a is a coefficient vector, which is a base function, and a, it is better right here, a1, dependent on xi. Coefficient vector. Okay, so for x, we can write x of t equals to this term. Here, this is rho transpose is a rho n times 1 vector, and h hat can be obtained by this. I row is a identity matrix of order row times row. This sign is Kronecker product. I row Kronecker product H transpose T, and here H hat of T is a row times row n matrix. Okay, look at this equation. We approximate x of t by using the eta-based function, and we have here the derivative of x, and we know that how to obtain the operational matrix of derivative, so we can approximate this term too. Okay, so for xi, the derivative of xi by using the operational matrix of derivative, and from this equation we can write H transpose of T. D, remember, D is the operational matrix of derivative I. And in general, we can write for a vector of x, we can write this. Where here d hat of t equals to I row Kronecker product of dt, and this is a row n times row n matrix. Okay, now by using this equation from here until here and substituting this equation in the main problem, we can write, I need it, so we can write h hat of t, d hat of t, a hat minus g of t. For x, we have h hat t, a hat, and for x, again we have this, but for this term we have this h hat t minus theta 1 of t and h hat t a hat. Okay, and for x dot we use this term h hat t minus t2 t and h hat t a times d h hat, yeah, t d hat of equals 0. And we show that this equation by W. W is this equation equals to 0. Now, we collocate this equation in the Chebyshev nodes. Chebyshev nodes can be obtained from this formula. Chebyshev nodes on interval 0 and 1 because we have, suppose that here we have t between 0 and 1. Can be obtained Chebyshev nodes from this formula. For j from 0 to n minus 1. Okay, by collocating this equation, we have here ti, or tj, it's not different. Okay, so we have a rho n system of nonlinear equations. Similarly, the matrix form for the initial condition x of 0 equals to x0. Is, I show that by V. H hat of 0, the initial condition on 0, minus x0 equals to 0. And now by replacing V in the last row, in the last row of W, we have a rho n nonlinear. We have a system or set of rho n nonlinear equation that can be solved by iterative Newton's method, and so we can find the elements of A, so we can find the solution of this equation x of t. We say that x of t is h hat of t times A. We know that about h hat is our base function, and we find that the element of A from solving this nonlinear equation by iterative Newton method, so we can find x of t, and it complex the numerical method. In this section, I want to talk about error estimate. We develop a new numerical method, and now we want to know about the error band of it. Here, for ease of exposition and without any loss of generality, we describe error analysis for the case rho equals to 1 and x1 equals x. At first, suppose that h mu of 0 and 1 be a Sobolev space for mu bigger than or equal 0 on interval 0 and 1. The norm function in Sobolev space can be obtained from this equation. So we have this theorem here. Suppose that X be a member of Sobolev space and Pn of 2t minus 1 be a well-known shifted Legendre polynomials. And suppose that this summation series n from 0 to n, an Pn 2 times t minus 1 and be a set of be the best approximation of x by using the shifted Legendre polynomials on interval 0 and 1. Here, pi on is the space of all polynomials of degree less than or equal to n. So we have this error band for this approximation. When we approximate x by Legendre polynomials, we have this error band for it. In this equation, the absolute value of x in Sobolev norm can be obtained from this equation. Okay, now we want to prove this theorem. We want to find the error band of eta-based function by using the best approximation theory. Suppose that X be a member of Sobolev space and for Pn be the eta-based function. Assume that Xn of t equals to this series. Now we have this error band for this approximation. Okay. Now we want to prove this theorem. Okay, now we want to find this x minus x n in Sobolev space. We have n here is from 1 to n. From the definition of eta-based function, we can write it in, remember, the series expansion of eta-based function. K from 0 to infinity, gamma k plus integer part of n divided by 2 plus half. Here we have divided by k factorial. We have in N2. Okay, we can write this term in this manner. N from 1 to n, here is n, an to pay attention here, call from 0 to m, this part, plus I want to write this series as this, from call from n plus 1 to infinity. By using the property of norm function, we can write it x of t minus call from 0 to m plus call from n plus 1 to infinity, this part. Okay, for this part, we know that the best approximation in L2 space is unique. So we have for this part, we have norm of xt minus n from 0, this part equals to here we have call from 1 to n, here we have call from 0 minus L2. Approximation by Legendre polynomials. And from the last theorem, here we have this error band for this norm, for this approximation. So we can write and n. So we can find the upper bound for this approximation. It remains to find the upper bound for this norm. Okay. We know that it is simple to show that call from 0 to infinity of this term. I don't write. This series is convergent for all y. So we have come from m plus 1 to infinity less than epsilon. Because of the property of convergency of this summation, we can obtain this easily. So here for this part, we can write a summation of to infinity epsilon. And by substituting this in this term, we can find the upper bound easily. And we find that it is less than, it is a simple computation and you can find it easily. Okay. We have another theorem here, and it's the last theorem that we are going to talk about in this session. And it's let X be a member of Sobolev space of order mu on interval 0 and 1. And suppose that X bar in H transpose R bar be the approximate solution of this equation by the proposed method in the section. So we have this upper bound for this. It is really easy to find that. We want to find the upper bound for this. And we know that it is less than x minus xn. Xn is the approximation of x. We use the upper bound of it in the last theorem plus xn minus xn bar. Here we have the approximation of x by using eta base function. Here x bar is the approximation of xn by using the proposed method. So we have two different xn here. From last theorem, we have the upper bound for this. So we should find the upper bound of this term. We have bar Vn2. I want to obtain this to the 2 in L2 space of 0 and 1. So we have here. Okay, we can write it. Two. And now by using the Schwarz inequality, we can write it in this form. And before we find the product of two eta function, and we know that here we have phi n to the 2, in theorem we find the product of 2 phi n. We have phi n of t times phi m of t. When n equals to m, we can find this easily, and by integration from 0 to 1 and substituting that, we can find these error band for the approximation of x by proposed method. Okay, I finished what I was going to talk about. If you have any comment or question, please let me know.